This video is a continuation of Unit 2, Part 1, Lesson 1 for Calculus. And in this video, I just want to talk a little bit about some interesting questions that might show up now that we're understanding or learning about derivatives. In this problem, we're talking about a function that's called capital G. And capital G is a combination of two other functions, lowercase f and lowercase g, so that 3 times the first function minus the second function will create this combination of functions called capital G. Combinations of functions are handy like this. Let's say, for example, I've got 3 fleet vehicles, and the cost to operate those vehicles is modeled by the function f. And because I'm, exporting the service maintenance requirements for those vehicles, I receive some sort of discount, and the discount formula is derived by using function g. So the combination of these functions can be used in the real world. I don't think that's what's happening in this particular example, but this is an example of where you might see that. So anyway, the functions on the right side of your screen are graphs that represent f and g. So we don't have the equations for f and g, but we do have a graph of each one of them. So we don't know what f looks like. We don't know what g looks. We know what they look like. We don't know what the equation for f is. We don't know what the equation for g is, and we don't know the equation for capital G. But here we're being asked to find the derivative, or the steepness, of capital G at some position 6. And so if we just remember for a second here that g of x is equal to 3 times f of x minus lowercase g of x, then g prime of x, the derivative of g, would be equal to 3 times the derivative of f minus the derivative of g. This is a direct result of our limit laws, which in turn gave us some of our preliminary derivative rules. 3 times a function, its derivative would be 3 times the derivative of that function. That's our constant multiple rule. So with this preliminary concept, once we have an understanding of that, we can now utilize that at the number 6. So 3 times the derivative of the function at 6 minus the derivative of the g function at 6. As long as we can evaluate those, then we should have a solution for g prime at 6. Well, here's 6 on our x-axis, and if we look up here, we have a function result of 3 for each of them, for both f and g. But remember, we're not looking for the function result, we're looking for the derivative function's result, and the derivative is talking about the slope. So what is the slope of the function f and g at the point value 6? So f is the function that's in blue here, and we want to know what's the slope of the line at 6. Well, it looks like that slope is equal to 1, so I'm going to change f prime of 6 to the number 1. And g prime at 6, well, that's this position here. It's a downward slope, and that's also a slope of negative 1. I'm getting this by looking at the rise and the run for each. Rise and run. So we went down 1 and over 1 to the right for the g function, so I'll call that negative 1. We went up 1 and right 1 for the f function at that point, so we'll call that positive 1. So we've got 3 plus 1, which equals 4. Without knowing what the capital function g is equal to, we are able to determine a little bit about its derivative at this particular point. Now, we would have a problem if the question asked for, say, g prime at 4, because that would require 3 times the derivative of f at 4 minus the derivative of g at 4. And that's going to be tough for us to do, because if we look at 4 on the x-axis, take a look at what's happening on each of these functions. Could you tell me how steep the line for g is at this point? Could you tell me how steep the line is for f at that point? That's going to be an issue. We can't do that because of the corner. So the derivative for g prime would have been undefined. At least g prime at 4 would have been undefined. Now, if one of these was able to be evaluated, that still wouldn't change our result. If we were able to find the derivative of f at 4, but not able to find the derivative of g at 4, then the derivative of the combined function would also be undefined. So having an understanding of derivative functions also tells us a little bit about parent functions and their derivatives as well. But we can also use derivatives in other ways too. Here we've got another function that's separate from the examples before, and this is a polynomial. And our job is to find all points on the graph of this function where the tangent line is horizontal. Now this would be a good no-calc question for our next calculus test, or a quiz before our next test. And the reason why I would say we would do this without a calculator is because we don't need to know what the exact shape of this graph is in order to answer question A, or B for that matter. Remember, when we say that a point that has a tangent line that's horizontal means that the slope of that tangent line is equal to 0. So let's kind of envision what might be happening here for just a second. We've got a positive leading coefficient with an odd degree, so I know the right tail of this function is pointing up, the left tail is pointing down. We could have as many as 2 turns because the exponent is 3. So we might have a graph that looks something like this. There are going to be some positions, or there could be as many as 2 positions where the tangent, the slope of the tangent line is perfectly horizontal. And we need to find the location of each of those. Now, keep in mind that it is possible for us to have a cubic graph that never levels off. This would be an example of a cubic graph where no points of tangency are equal to 0, and we don't really know what this particular graph is going to look like. So without looking at the graph, we can evaluate it, we can interpret it by using our calculus. So all questions that are like this, that are posed in this way, start with a derivative. So we know that the original function was f of x equals 2x cubed minus 6x squared minus 90x plus 5. The first thing that I'd like to do is find the derivative. And using the rules that we started to establish last week, we can use a series of power rules that are added and subtracted with one another. And recall that the power rule says that we bring this exponent down and multiply it by the coefficient and reduce the exponent by 1. So that happens in 3 of these cases. We technically have an exponent of 1 here, so that can come down. And then we've got a constant at the end, which hopefully you recall the derivative there. Well, in this first group, 3 times 2 is 6. Reduce the power by 1, and we've got 6x squared. The second one is going to be 2 times negative 6, which is negative 12x. We're reducing the power by 1, 12x to the first power. 1 times negative 90 is negative 90. Reduce the power by 1, we get x to the power of 0. X to the power of 0 is just 1, so we don't need to display that. And the derivative of a constant is 0 itself. So now we have a derivative function. This derivative function tells us the steepness or the slope at any x value of the original function. We know the slope of this original function at any point now based on the derivative rule that we just established. So if we want to know when the slope of our original function is equal to 0, we simply set the derivative itself equal to 0, and we solve. There are lots of ways to do this. If this is a no calculator question, hopefully I've given you one that can be factored. And as it turns out here, 6 is a common factor. We can divide each of these by 6, which is good. Minus 2x minus 15. And the remaining expression can be factored still. We've got a standard trinomial inside this group. So I'm going to use an x, and I'm going to guess that 5 and 3, specifically a negative 5 and a positive 3, will continue factor. And then lastly, because these factors multiply to equal 0, then x itself has to be negative 3, or x is 5. These are the 2 positions where the slope of the original function is equal to 0. Now that gives us our x values, but it would be nice to know what the actual position was, because the instructions did tell us to find the points where the graph has a tangent line that is horizontal. So let's jump up here and now evaluate the function at -3. Notice I'm using the original function at this point, and the function at +5. Now here's where I think a calculator might be permitted if I ask you to go this far, because if I evaluate 2 times -3 cubed minus 6 times -3 squared minus 90 times -3 plus 5, that's going to be tough to do without a calculator, or at least too time consuming. So evaluating that and showing that it equals 167 I think would be fine for a calculator portion of a test or a quiz. But everything leading up to that I think can be done without a calculator, including finding those x values a moment ago. And for our second point, we just substitute the number 5 in place. And if we were to evaluate that, we get a result of -345. So again, we don't know a whole lot about this particular function, but now we know that at the coordinate -3, 167, which is up here somewhere, let's say, and then at the point 5, -345, so over here, way down here, we know the graph has leveled off. In addition to knowing that this left tail is pointing down and the right tail is pointing up, and the fact that we've got a y-intercept of 5, we knew that from our analysis of polynomial functions last year. We've got a data point here at 5. We're starting to get a pretty good picture of the behavior of this graph. And what might have been a complete unknown when we first started, well, we're starting to fill in the blanks here, and we're starting to understand exactly what's happening in the behavior of this function. And all of that is thanks to calculus. So I'd like for you to try part B on your own. We're doing much the same thing, finding all the points on the graph where the tangent line, instead of having a slope of 0, now has a slope of 120. So pause the video now and try this on your own. You can resume playback in just a moment to check your work. And there we have it. Evaluating the derivative and setting it equal to 120 allowed us to find our ultimate solution. Now keep in mind that whenever we solve a polynomial equation, the best thing to do is to make that equation equal to 0. We didn't have 0 equals at the beginning, so I subtracted 120 from both sides and was able to factor to find solutions for x. Once the solutions for x were identified, we substituted them back into the original function to find the position of the point. And so when x was equal to -5 in the original function, we had a y value of 55. And when x was equal to 7, we had a y value of -233. So if we compare that to the sketch we had just a moment ago, -5 is somewhere over here, and we're saying that the slope at this point is equal to 120, whereas the slope here was equal to 0. The slope here was equal to 0, and then at an x value of 7, we had a slope equal to 120. You might be asking yourself, well, what about the position in between these two high points and low points, between the local max and local min? Isn't there a point over here that has a slope of 120? Well, sort of, yes, but remember that since it's a downward facing slope, we would say that there's a slope of -120. And a point like that does exist, and you could find it on your own if you're so inclined. Well, I hope this video helps illuminate some of the uses of our derivatives. If you have further questions, please let me know. Thanks for watching.